Thank you very much for coming. It's a real pleasure to be here. Thanks to the organizers. It's such an amazing event. One of the areas in computational social science is concerns about using social theories combined with mathematical tools and data sciences to understand success. I feel very fortunate to be able to involve in this direction, and I'm very excited to share with you a few stories that we have learned over the past 5 years. Okay, so here's what I'm going to do today. I'm going to quickly go through roughly about 4 studies. 2 are published, so it's old, but you have paper to look up to. Then the other 2 is just finished, so in the hoping to be published category. And to do all of this, let me first turn into a meteorologist to give you a broader picture. This is a typical weather report you see on TV. Many of you, if you happen to be living in the East Coast, you would remember this hurricane. For those of you who don't know, are not familiar with this, let me tell you exactly what this means, right? This literally means for a hurricane started from Caribbean, people in New York know well in advance when this is gonna hit New York, with what kind of probability, what will be its intensity when it hits. Right? What this also means, when it comes to natural phenomena, we're great. We have developed a very comprehensive understanding based on massive amount of data we have collected and multiple types of models and algorithms that we build on this data that we now believe natural phenomena can be measured, modeled, and predicted. Right? So no one will argue against you about that. And there are many benefits of this, of course. One is to avoid being this person, right? If you see the hurricane in front of you, it's too late. What you want is that kind of predictive power bestowed upon you by the data and model that we have built to help you make more informed decisions. So when I think about this example, I immediately relate to another example in a way or the other that's very, very similar. That is when we think about success. When we think about success, we always think about the value or impact in the future. Think about you're making an investment. You're looking at the price trajectories, you're looking at a portfolio, you're looking at the competitors, what they are doing. But what you're really thinking about is this price going to go up or down in the future? Think about you're going to hire someone, right? You look at the CV of this person, the LinkedIn profile, Google Scholar profile, all those beautiful things this person has done in his life. But what you're really thinking, that only question in your mind is this person will be successful or not 5 years, 10 years down the road? So, but there's one important difference between the 2 examples I just gave you, is that when it comes to success, we often still just rely on qualitative judgment. Yet it just seems to be notoriously hard to do so, even for experts. This is a great quote I like from Thomas Edison, 1889. Fooling around with alternating current is just a waste of time. Nobody will use it ever. Interestingly, about 10 years before he said this, he was the one that finished the first successful test of electric light. So he was a very expert on electricity back then. So you got to listen to him, whatever he says, right? So multiple examples like this make me start to wonder, with availability of big data in multiple domains now captures individual performance and impact, can we now take a quantitative point of view towards success? Are there quantitative signals behind success? Are there predictive signals? Hopefully early signals behind success. Come one day we look back, hopefully 5 years down the road, and we look back today and say, you know what, success can also be measured, modeled, and predicted, just like the way we conquer the natural phenomena. And obviously this is an unrealistic optimism, but our optimism came from the fact that we recognize success is fundamentally a collective phenomenon. You are successful not because you say you're successful, your parents say you're successful. You're successful because everybody else has to agree. So success is not about you, it's really about us. If we accept the collective nature of success, then there must be fingerprints in the data set that captures the collective response to a new technology, new innovation that we can now detect using tools of data and network sciences. Okay, so I'm going to show you a few examples. I'm going to start with an area where success is relatively well defined and relatively well documented. Some of us call this area science of science, and this is an area where we have a lot of giants and founding fathers in the field, including Robert Morton, the theory of Matthew effect, singletons and multiples, including the solar price, the theory of power laws, and as well as Thomas Kuhn, scientific paradigms. what I'm going to do in this area is to stand on the shoulders of these giants, but take two things that they did not have the luxury to have. Number one is the massive amount of data now available capturing multiple activities of science, many of which these giants did not even imagine could become available to us. Number two is make use of the tools and techniques being developed in artificial intelligence or fields like network science to start making sense of these data that are available to me. Okay? So the first question I'm going to ask is to treating based on a common consensus, think about citation as an approximation for the success of a discovery, and asking the question, is there any predictive signal in citations? So it all starts with this one single figure, where I randomly selected about 200 papers from a physics journal. X-axis is time. Y-axis tells you how many citations each paper has going forward. There is one single message in this figure that this is a mess. If I ask you, let me block part of the screen and just look at what's happening here, can you tell me then what's going to happen in the future? The answer seems to be hopeless. So the first question I'm going to ask then is the following. Is there a mechanistic model based on verifiable assumptions from data that can generate a system that looks just like this? So it turns out there is. There are three factors that are known to influence the way paper is cited. Number one is preferential attachment, people are very familiar with. Number two is aging, that is, recent papers are more likely to offer fresh ideas, but with time, its impact is expected to fade away because its novelty becomes part of the common knowledge. Number three is paper differs in terms of their inherent quality or size of the community. So the typical mathematical treatment is to assign a constant parameter to each paper. If we acknowledge there's three kinds of mechanisms, we can actually combine them to calculate what's the probability for a paper to get cited. That in turn allow us to write it in the read equation formalism that help us calculate what is the expected change of citations for each paper as more papers are getting published. And luckily, this model can be analytically solved. So we arrive, after a couple of pages of math, we arrive at this one single formula with three parameters. This formula is right here. The three parameters are fitness, tells you how high it jumps. Immediacy tells you how quickly you're getting the attention. And longevity tells you how quickly that attention decays over time. Okay? Now, let me remind you, what I just said make a remarkably strong prediction, because this means as noisy and diverse as citation dynamics of indie papers we saw, they all follow the same universal formula. And the differences between the papers are simply the differences in terms of the three parameters. So that means if I chose 4 papers for their obvious diversity in citation dynamics, and if I learn the fitness, immediacy, and longevity parameter and rescale their citation dynamics, they should all follow the same universal line as we can predict analytically. Now people say, Dashun, you're trying to trick me with the 4 papers carefully selected. So there's about 8,000 papers in physics and 1,000 papers published by Nature in a year. So there are obviously deviations, but given how noisy the data was and how clean the collapse is, I think this amount of universality was very surprising to us. So what this means is that now we have a model that can generatively generate a bunch of citation patterns and citation networks that will produce a system that just looks like the real system, but smoother, right? So there are a bunch of things you can do once you exploit this level of predictability, because for one thing, you can take now a weather forecast approach, right? For any given paper, if you know the citation history, you can then learn what is the likelihood for this paper to be captured by fitness, immediacy, and longevity parameters. And that estimation in turn translates this cone of predictions to tell you what's the likelihood for this paper to get a certain level of citations. And you can do this as long as you have the citation history. Increasing the training window, you see 2 things happen. The cone shrinks. It become accurate, and this is obvious because the hurricane is now in DC, so not too far from New York, so you know better where this is gonna go, right? So that was the first quick study I wanted to go through, but moving forward, I want to think about, if I think about career as a combination of multiple papers published at different times of your career, now I want to think about if I start understand each of these items, can I now say something about overall the Google Scholar profile we've all been staring at every day? mostly about others. Can we now learn a little bit about this and think about how to understand it, right? So I want to talk about quickly 2 studies about this. And the opportunity is really there's a bunch of data that's now available, right? So the first study I want to think about is there other quantifiable signals of an impending scientific hit in your career? And will scientists produce another high-impact work following a major breakthrough? So this is what I broadly call the HOPE project. Is that are there still some hopes left, or are we dead, scientifically speaking? So the way we want to represent the career in this study is to think about a career as a bunch of job pins right here, okay? Each job pin indicates the location where you publish a paper along your career, and the height of that job pin tells you how good that paper is measured by 10-year citations, okay? Now, first question we're gonna ask is, given this representation of a career, now a very well-defined quantity is I can find your best paper in your career, the highest job pin for you, that's your personal best in your career, and I'm gonna ask, where does that occur in your career, okay? So I can plot this for a bunch of people to think about what's the timing of that peak, of that hit, and what you see typically is some pattern like this, and peak somewhere in the middle of your career and starts to decay. And this is heavily captured by the innovation literature, and I'm not here to argue about the shape of this curve. Commonly, people say the decay is because of the tendency towards retirement and also administrative duties. I'm not here to argue about the shape. What I'm going to do is do a simple experiment right here. Given the real career, this job pins, what I'm going to do is for each career, we're going to keep their locations are all fixed. I'm just going to randomly start swapping them, okay? I'll keep the height, keep the number of pins. I'm just going to, for everybody, going to random swap them. By doing this, the only thing I'm trying to break away is the timing when that should happen, right? So once I do that for everyone in my database, and then I'm going to replot this distribution again, I'm going to see how different it looks. And this is the randomized version. What do you see? They fall right on top of each other. So what this means is that when it comes to your best paper in your career, it can happen any time in your career. It may as well be your very first paper, or may as well be your very last paper. It does not matter. This is what we call the random impact rule. The reason you see the deviation in the shapes is really just because you publish more. So if you publish more, you're more likely to see a hit around that time frame. Okay, so this also means there's still hope, right? Keep publishing. Very important. Okay, just take away this, that'll be good. And this is a collaboration with Roberta Sinatra. It was published recently at the end of last year. But there are other results in that paper I won't have time to get through. I will actually go into detail about one major implication of this discovery. Is the reason question then what happens if I publish a big work, right? Because the random impact rule seems to tell me if I do a big work and then going forward, this is, again, just random. So that supports the viewpoint of regression towards the mean. But the Matthew effect tells me winning begets more winning. So if I do it right, then I got something. I got it. So I learned that I should be more likely to do a major work. So this leads us to ask a very interesting question recently. Is this question, does hot hand exist in creative careers? My student Lu Liu started to assemble a bunch of creative careers, including more than 3,000 artists, and their artwork measured by hammer price in the auctions, more than 6,000 movie directors, all the directors in IMDb, and all their movies they have ever directed and produced, and measured, also quantified by the IMDb rating, and obviously also 20,000 scientists. And what we wanted to ask, the first question was, if I know where your biggest work is in your career, where would your second biggest work be? And we measure it across all kinds of careers. We find a very universal phenomena is this clear diagonal pattern across different kind of careers. Is that once I know where your biggest work is, I know very well your next biggest work will be. It's somewhere just around the corner of that work. What these, and then we have a bunch of other empirical observations, all points to the same message, is that what we realize is that Along your career, if you think about this is on average how good a paper you will produce as a scientist, it roughly stays constant. But at a certain point of a career, all of a sudden you went to like a super saiyan if you're into Japanese cartoon. It's like you're not yourself anymore. All of a sudden you're elevated to another level and going at sustained on that level before you fall back down to where you began. Okay? And this is a pattern we realize very surprisingly seems to apply all the people we look at. And this is very surprising. And what we find by fitting the model to the data, what we realize is a couple messages. Number one, the hot hand period is ubiquitous. More than 90% of people in our data set in each of the domains have at least one hot hand period. Now, don't be so happy. Number two is that hot hand period is very unique. Most people who have hot hand period have just one. And the hot hand period seems to be rather temporarily localized, roughly lasts about 4 to 5 years, and then that's it, you're back to where you were. Okay? So this seems to start painting a picture of cherishing the moment, isn't it? Because if you have one hot hand period, try to publish more in that period. And this period obviously appears randomly in your career. And what we also realize is that because of the ubiquity and uniqueness of hot hand period, your career impact, the collective impact you see on the Google Scholar profile, that curve is fundamentally determined on whether or not you had a hot hand period or not. So now we have analytical calculation, analytical model, closed form solution for the Google Scholar profile now. So what this actually tells us is that if you don't consider the hot hand period, then that will lead you to systematically overestimate the future impact of a scholar if the hot hand period occurred early, and underestimate a scholar if a hot hand period has not occurred. So obviously very important for personnel decisions such as hiring, promotion, and tenure. My last story, I'm going to shift gear a little bit. My last story starts with this single picture. And this picture was published 4 years ago by NBC. This is the Pope picture. And when I saw this picture, it fascinated me because I felt, oh, there's something very profound about this. But I kept staring at this for 3 years with my student, poor students, Qing Jin. For 3 years, we couldn't lay our finger on what exactly is profound about this. Until I realized this. Let's do a quick show of hands in the room. How many of you have a cell phone in your pocket right now? Okay, this is just trying to see who is alive, awake, good. Thank you for being awake. Now, how many of you now have 2 cell phones in your pocket at this moment? Yeah, trying to see who's rich, good. So, what I realized was profound about this picture. It's not about people didn't use iPhone, and now people use iPhone. What's interesting is because all these people there, they had a phone in their pocket. They were using something, and now they're using something else, right? Well, by the way, it's interesting. This guy's trying to take a picture. See, very advanced. So this seems to tell me the adoption of iPhone. By only thinking of adoption, that seems to be an incomplete picture. Because now if you look at a lot of canonical examples, even go all the way back to Rogers, Iowa cornfield, you see a lot of the adoptions are not really adoptions. They are really just substitutions, right? Once you put a pair of a glass of substitution, you look at the world again, you understand a lot of phenomena we think about is about substitutions. Think about buying a phone is like this, buy a car is like this, buy a house is like this, buy a personal computer is like this, develop a healthy habit is like this. You have to break away from the old habit, think about the renewable energy, think about the electric vehicles. All of this is about substitutions. Not everything is substitutions, but many things are. Now, so the question I had was, then how the systems that are driven by substitutions look like? So there are many research about the diffusion process ranging from epidemiology and diffusion of innovation. All of the models point to one common assumption, that is the initial adoption curve follows a multiplicative process. You start with a seed, then you multiply from there. So that means the initial very early stage growth pattern should follow an exponential function. Okay, so I wanted to test this hypothesis in the area where I just showed you the cell phone example. So I collected all the cell phones and centered them around from the first day they are launched and measure how many phones were sold every day after that. And they are in this picture. There's 3 messages in this picture. Number one, all this curve look like a straight line on log-log plot. That means the growth patterns follow a power law. Number two, all these different hindsights, they're each of their own lines, they have different kinds of exponents. They have hindsight-specific exponent. Number three is that most of these exponents, they are non-integers. So I will come back to that in a second. Because before we get too excited, let's think about, is this just about hindsights or some other system also look like this? So when we went ahead and collected other data in other domains, so we collected all the sales data from in automobile in North America. The 0 point is when the car is launched, and then we calculate the sales. It all looks like the same pattern. We went ahead and checked all the apps. The moment you hit Apple App Store, we check the downloads of each app, and then you check that, you see it follows pretty much the same pattern. So what this means across all the systems that are driven by substitutions, it seems like the early growth pattern do not follow exponential function Hasmeri in spreading phenomena. Instead, they follow power law with non-integer exponents. Power law with non-integer exponent growth is a very odd phenomena, almost never predicted by most models we have seen because it's a non-analytic behavior. Let me tell you exactly what I mean. If you do the Taylor expansion of a power law with a non-integer exponent around t equals to 0, it diverges. Therefore, most models, epidemic models, SIR, or other models, or analytic models will not be able to generate this. And what the power law growth means is that at t equals to 0, when the app hits App Store, when your iPhone launched the first day, there's an explosive adoption process. But once you enter the market, it grows much, much slower than the exponential growth. So all of this discovery asks us one major question is, then what mechanisms are responsible for the observed power law growth? Okay? So it turns out it's very hard to do this because substitution patterns are very difficult to trace empirically. Luckily, the hindsight data I told you provides one of the most ideal settings to do this because anonymized phone numbers together with portability across devices tell us exactly this is the individual, this person was using this phone and was using the next phone. So we went ahead to collect the 3.5 million users across the whole country and trace their usage pattern for every day over 10 years. And together we have about 9,000 hindsights in total. What you see is that every year, although the hindsights are changing, every year there's a fixed number of hindsights enter the market. It's a very competitive picture, isn't it? Because new hindsights are coming in, same amount. In turn, they drive the popularity of existing hindsights, right? So what then you allow us to construct is this new kinds of map of substitution patterns where each node is a phone and the links are connecting them in terms of who substitutes who what, right? So the color of the link indicates the destination of the phone for substitutions. So you can see this is a system where it goes through a dramatic transformation from feature phones to smartphones. So most people are substituting for iPhones or Android phones, right? So my question is, given a picture that is so heterogeneous and complex, is there a mechanistic model that can help us capture the dynamics of this kind of system? And the good news today I will show you is that there is. If you formulate this problem in the rate equation formalism, that is the number of users using certain phone, is essentially all the substitution flows going from all other phones to this phone, minus all the people go from this phone to all the other phones. So if you do that, then the key is just to calculate the substitution probability. What's the probability for hindsight j to replace hindsight I? From our detailed data set, we're able to discover there are 3 mechanisms determining that: preferential attachment, recency, and the inherent propensity between hindsights. Once we know this, it actually allows us to, again, have an analytical calculation of the inherent life cycle of each hindsight in the system, again captured by 3 parameters. Anticipation quantifies how many people buy on the first day. This is a very important indicator because of the power law behavior. Fitness tells you what is that power law growth pattern, and longevity somehow tells you what is the typical characteristic time for you to be replaced by subsequent innovations. There are many things you can do once you have this analytical framework. I'll show you one example. Is that what this means is, again, like the citation case, this means all of these phones, automobiles, and apps, they could all look different, but they all captured by the same universal function. So if we can learn the 3 parameters and rescale them, they should all follow the same universal function like what we showed here. So this is actually very, very surprising to us, because this is saying not only all different handsets follow the same universal line, handsets, automobiles, and apps, because they are all items in complex substitutive systems, they are actually all following the same universal function, and the differences between them are simply the differences in terms of anticipation, fitness, and longevity parameters, right? So quickly summarize the last study. I went a little bit more detail in. Number 1 is an empirical observation. We find that the impact in substitutive systems grow not as exponential, but a power law. And second, exploring a real data set, we find 3 mechanisms governing substitutions. This is among the first empirical observational substitutions. Third, these observations allow us to develop a new model that not only observe the growth pattern, but also collapse different kind of trajectories into one very tight curve. Okay, this is the work by my student, Qing Jin. And let me close my talk with a little story called 10%. If you're into oil drilling business, I'm suspecting none of you are. If you're into that, and 10% is a number you're very familiar. 10% is the success rate for us to strike oil back to World War I, right? So your instinct tells you there might be oil somewhere. You go ahead and waste 90% of your time drilling dry holes, right? Because of, not only to mention the tens of millions of dollars cost for each drill. Because of profitability of oil drilling business, we tried many things to improve that. But this number stayed remarkably stable over time. Over the next 75 years, however, we have seen a 6 times increase. Now we have a 60% success rate of drilling oil. So what happened, you may ask? It turns out it's not what the petrol engineers did. It's really a bunch of geologists who had no idea what oil drilling business is, but they were just develop theories to try to understand structures deep underneath the earth that turns out to be the necessary conditions for oil. We still don't have the 100% guidance for drilling oil, but now 6 out of 10 times we'll strike oil. But equally important is the fact that even if when we fail, we now start to understand why we fail. So a lot of people ask me, why would a physicist care about a success? I think, in a way, it's kind of what we hope is to try to provide to innovators, entrepreneurs, scientists, policymakers, and administrators the same kind of useful theories that geologists once brought to oil drilling business, right? We don't have the 100, so therefore understand success is not about the 100% success rate. It's really try to understand the mechanism behind the success. And once we understand the mechanisms, then hopefully we can make predictions predictably successful, and maybe develop metrics that are quantifiably reliable. So thank you very much for your attention. This takes a village. And